In the previous video, we set about fitting a structural regression model to data from a study on latent cognitive abilities of high school students. Latent cognitive abilities are those which cannot be observed directly, but which are manifested in ways that can be observed. Part of the model fitting process is assessing the fit of the model to the given data, and in this case, the model did not fit the data well. This can happen when a model does not have the right kind of terms, or when it has too many built-in constraints and, as a result, is not flexible enough. When this happens, natural follow-up questions would be, in what ways does the model not fit the data well? Can the model be extended, or can it be loosened up in such a way that it becomes flexible enough that it does provide a good fit to the data? In this lecture video, we're going to use residual analysis to identify in what ways the initial model does not provide a good fit to the data. In general, a residual is defined to be, and calculated as, the difference between an observed datum and the model predicted value of that datum. When we have access to the raw data, which we might more accurately call case level or subject level data, or in this case student level data, we can calculate a residual for each student level observation in the dataset. In this example, however, we did not have access to the student level data. Rather, the information we did have access to consisted of the sample sizes and the observed sample covariance matrix, and it was this information that was used in fitting the model. Because we don't have student level data, we are not able to calculate student level residuals. So in this kind of a situation, what do we mean by a residual? When we don't have access to subject level data, how are residuals even defined? And how can a residual analysis be done? Recall that when a sample covariance matrix is used as the raw data for fitting an SEM, the goal is to find parameter estimates such that the resulting model predicted covariance matrix is as close as possible to that observed sample covariance matrix. As stated previously, in general, a residual is defined to be the difference between an observed datum and the model predicted value of that datum. In this case, an observed datum is an entry in the observed sample covariance matrix, and the model predicted value of that datum would be the corresponding entry in the model predicted covariance matrix. With this in mind, the residuals consist of the set of differences of corresponding entries in the observed sample covariance matrix and the model predicted covariance matrix. A matrix of these differences, that is, a matrix of the residuals, is obtained by calculating the difference between the observed sample covariance matrix and the model predicted covariance matrix. Entries in this difference matrix that are large in absolute value correspond to the entries in the sample covariance matrix that the model is not doing a good job of predicting. Therefore, to identify the ways in which the model is not fitting well, we locate those entries in this residual matrix that are large in absolute value. The corresponding entries in the sample covariance matrix are the entries that the model does not predict well. Each entry in a covariance matrix corresponds to either the variance of a manifest variable or the covariance between a pair of manifest variables. Once we have identified an entry in the sample covariance matrix that the model does not predict well, we can determine the manifest variable or pair of manifest variables that entry corresponds to. If we then consider what these variables represent, the behavior we expect them to exhibit, and ways in which the variables may be related, we may be able to glean some insight into how to extend or relax the model in order to improve its fit to the data. This is the approach we are going to use in this lecture video. So here's an outline of what we'll be looking at in this video. We'll first obtain the residuals from the initial model. we'll perform an analysis of the residuals to determine where the problems are and what their causes might be. So we'll ask and answer the questions, where is the problem and what is causing the problem? We'll then extend and/or relax the constraints in the model based on what is learned from the residual analysis. And then finally, we'll fit the new model and assess its fit. So let's jump in. So let's first look at where we left off in the previous lecture video. So here is the path diagram for the structural regression model that we fit in the previous video. Here is the summary from that video. The structural regression model was specified to Procalus using the LinEQS programming language. The model was fit, the parameters were estimated, and all indications were that the model was specified correctly. Now, let me just say that when I say specified correctly, what I mean is that the model was specified to the SEM software correctly. We need to make sure that the model we're wanting to fit is the model that was actually fit by the program, and so that entails ensuring that the specification of the model to the software corresponds to what we intended. However, several model fit indices indicated that the model provides a poor fit to the data. The model is not flexible enough to be able to fit the data well. The model not being flexible enough is not a good starting point for the subsequent model simplifications that we ultimately want to investigate. And so the next step is to find a better fitting model. So in what ways does the model not fit the data well? And what can we change about the model so that it does provide a better fit? Let's first obtain and analyze the residuals from the model. So here is the SAS code for the initial model. And notice that I've added, prior to the invocation of Procalus, the ODS output statement. And this is going to create a data set that contains the residuals from the model. The residual option requests that residuals be displayed, and the pcore option requests that the predicted covariance matrix be displayed as well. Now, in addition to the SAS code to fit the model, I have this additional SAS code. The code in the data step calculates the absolute values of the raw residuals and their ranks. The proc print statement prints a listing of the absolute residuals that were calculated in the previous statement. And finally, the gplot statement constructs a plot of the absolute residuals ranked in descending order of their magnitude. So let's talk about residual analysis in the context of an SEM like this. Let's remind ourselves how we calculate residuals in the context of a structural regression model. Recall that the sample covariance matrix, S, serves as the raw data for the analysis. Associated with the model is what is called a model-induced covariance matrix, which we're denoting by sigma. For every possible fitted model, there is a predicted covariance matrix denoted by sigma hat. The structural equation model is fit by finding estimates of the model parameters that make the predicted covariance matrix, sigma hat, as close as possible to the sample covariance matrix, S, where close is defined by the particular model fitting criterion being used. Once the model has been fit, the matrix of residuals for the model is obtained by subtracting the predicted covariance matrix from the observed sample covariance matrix. So the matrix of residuals is equal to S minus sigma hat. So here is a visual demonstration of this calculation. In the upper left, we have the observed sample covariance matrix. From that, we subtract the model predicted covariance matrix, and the result of that subtraction is the matrix of residuals. Taking a closer look, here is the observed sample covariance matrix. This is the predicted covariance matrix. And when we subtract the predicted covariance matrix from the sample covariance matrix, we get the matrix of residuals. And so it is the entries in this matrix that we want to look at. So where is the problem? We want to focus on the largest residuals. So here are the signed residuals ranked in descending order of their absolute values. The largest residual is associated with the covariance of V6 and V9. And you can see here that the residual is about 9.13. Now here are the entries in the matrix of residuals that correspond to that value. We can see that this residual of 9.12555 is associated with the covariance of V6 and V9. Now here is a listing of the absolute values of those raw residuals. This slide gives a plot of those absolute raw residuals versus their ranks. The largest absolute residual is equal to 9.12555. The next largest is just a little bit larger than 5. And look at that drop off. The largest absolute residual is quite a bit larger than the rest. So again, looking at the listing of absolute raw residuals, we see that the largest residual in absolute value is 9.12555. The next largest is 5.10613. We see here that the largest absolute residual is approximately 80% larger than the next largest residual. Let's look for and work on addressing the cause of this large residual and then refit the model. If the resulting model fits well, then we're done. If not, then we can always look for additional issues to address. This residual is the difference between the sample covariance of V6 and V9 and the model predicted value of that covariance. In a previous table, we saw that the signed value of this residual is positive. And so this tells us that the predicted covariance is much smaller than the observed sample covariance. Now, what do we know about V6 and V9? This is going to help us answer the question, what is causing the problem? So let's do some detective work. Here is a table of the manifest variables that we looked at when we were fitting the model in the previous lecture video. We see here that V6 and V9 are repeated measures of the third figural relation score. Maybe there's something about the third figural relation score measure that causes repeated measurements to be more highly correlated than they might otherwise be. If so, perhaps if we allow the two repeated measures V6 and V9 to be more directly linked in our model, the model will be flexible enough to more accurately estimate the covariance of V6 and V9. How can this be accomplished? Well, we've got to be a little careful how we do it. So let's look at fixing the problem. Now, do you remember Raykov's 6 rules? 2 of those rules are pertinent here. Rule 4 says that covariances between dependent variables are never model parameters. Because V6 and V9 are dependent variables, by Rule 4, their covariance is not a model parameter, and so it would not be appropriate to include a covariance term for them in the model. Rule 2 says covariances between independent variables are model parameters. This rule includes the exogenous error terms. And so by Rule 2, the covariances of E6 and E9, the error terms associated with manifest variables V6 and V9, is a model parameter. And so by Rule 2, we can allow the error terms E6 and E9 to have a non-zero covariance. Doing so effectively allows V6 and V9 to be correlated indirectly through their error terms. So let's look at an updated path diagram that allows for this kind of extension. So here is the path diagram for the initial structural regression model. In this initial model, notice that the only connection between V6 and V9 is by the impact on each of factor F2. The impact of F2 on V6 is direct, whereas the impact of F2 on V9 is indirect through factor F3. This may very well be the cause of the underestimation of their covariance. Perhaps we can improve things a bit if we allow a more direct connection between V6 and V9 through their error terms E6 and E9. And so we've included a two-way arrow between E6 and E9, and it's got an asterisk on it, so we know it's a model parameter. Now, this is a reasonable rationale in the context of the underlying theory of what's being researched here. Again, V6 and V9 are repeated measures on the third figural relation score. Now note that by the same rationale, we might expect V4 and V7 to have non-zero covariance as well as V5 and V8. Now, why is that? Well, because in the same way that V6 and V9 were repeated measures on the third figural relation score, V4 and V7 are repeated measures on the first figural relation score, and V5 and V8 are repeated measures on the second figural relation score. But while the residual associated with the covariance of V4 and V7 does make the top 5, with a value of about 2.58, its magnitude is less than that of residuals for the covariances of variables we would not expect to be correlated in this way. In particular, V4 and V9, V3 and V6, and V5 and V7. Furthermore, the residual associated with the covariance of V5 and V8 does not even make the top 10. Now, we need to keep in mind that residual analysis can lead down a seemingly never-ending rabbit hole. And so let's start by focusing on accurate estimation of the covariance of V6 and V9 and worry about the other two covariances only if necessary. Next, let's look at extending the model. We've done this by using the cov statement to add a name or label for the covariance of E6 and E9. This allows the error terms E6 and E9 to have a non-zero covariance. Next, let's look at the path diagram for the fitted extended model. So here is the path diagram for the fitted extended model. Notice the two-sided arrow connecting E6 and E9. This allows them to have non-zero covariance, which is estimated to be 12.26 and is highly statistically significant. Given their estimated variances, this corresponds to an estimated correlation of almost 0.5. And so allowing E6 and E9 to be correlated appears to be practically significant as well. Here's a close-up showing the two-way arrow between V6 and V9. Now we need to keep in mind that this actually represents a two-way arrow between the error terms E6 and E9. And we also see the estimated covariance of 12.26. Has this model extension mitigated the problem of estimating the covariance of V6 and V9? Well, let's take a look at that residual. So again, here is the observed sample covariance matrix. And we see that the observed sample covariance of V6 and V9 was 59.52. Here is the predicted covariance matrix for the extended model. And we see here that the predicted or estimated covariance of V6 and V9 is 59.42. Taking the difference, we get a residual value of 0.1. So whereas this residual was a little bit more than 9 for the initial model, for this extended model, we've reduced the residual down to 0.1. Again, the observed sample covariance of V6 and V9 was 12.52, and the predicted value is about 12.42. So we're predicting it very, very well. So has this model extension mitigated the problem of estimating the covariance of V6 and V9? Absolutely. Now what about the other residuals? Let's take a look of a plot of the top 10 absolute residuals for the extended model. And so here is a plot of the absolute raw residuals versus rank for the extended model. And look at that drop-off. Now, at first glance, this plot looks just as bad, if not worse, than the first plot. But notice that on this plot, the vertical axis has a much smaller range, from 1.4 up to about 3.5. Much smaller than the range in the first plot, which went from 0 to 10. Here's a plot of the same values, but with a vertical axis that has the same range as that of the first plot, which ranged from 0 to 10. Things look much better in relation to the first model from this perspective. And so here is a listing of the top 10 absolute raw residuals for the extended model, and you can see that these are much more comparable. So let's assess the overall fit of the extended model. And so again, looking at the path diagram for the fitted extended model, we've got a table of fit indices in the bottom right-hand corner of this plot. And so let's take a look at these values. First, we see that the chi-square value for this model, 20.55, is less than the model degrees of freedom, which are 23. The model chi-square p-value, which is 0.61, is quite large and therefore insignificant. The adjusted goodness of fit index, which is 0.96, is at or above the midpoint nines. The comparative fit index, which to 2 decimal places is 1.00, is at or above the midpoint nines. And finally, the root mean squared error of approximation, which rounded to 2 decimal places is 0.00, is less than 0.05. And so therefore, the model appears to fit the data very well. So to summarize, the initially specified structural regression model that was fit in the previous lecture video did not fit the data well. Residual analysis revealed that the biggest problem was in predicting the covariance between manifest variables V6 and V9. Review of Raykov's rules showed that the proper way to relax the model to allow more flexible estimation of the covariance of V6 and V9 was through the covariance of their error terms E6 and E9. The structural regression model was extended to allow for the covariance between error terms E6 and E9 to be non-zero. The model has been specified to, that is implemented in, the SEM software correctly, and the fit indices indicate that the model provides a very good fit to the data. And so the next step, in line with the principle of parsimony, we're going to begin looking for ways that the model might be simplified. But that's going to have to wait until the next lecture video. I'll see you then.